right, how's everyone feeling today?
Totally awesome.
Alright, that's what I like to hear, ladies and gentlemen. So, today I want to share a little lesson on the equation of continuity. And basically, folks, it says, if you have like a long pipe, and basically, let's say you have some sort of fluid going through the pipe, like water, yes? Well, if you look at any two cross-sectional areas of this pipe, even if it goes from like a fat pipe to a skinny pipe, if you look at a cross-sectional area right here, right there, yes? And then you compare it to another cross-sectional area, say this is area 1 right here, and this is area 2 right here. Basically, it's like a conservation law. And it basically says, however many gallons of fluid go through over here, that's how many gallons of fluid go over here. That's how many gallons of fluid go over here each second. So, for example, if you have, 55 gallons going through the pipe over there, per second. Must be a really fat pipe, but 55 gallons per second, yes? Well, if this is a continuously flowing liquid and all, then over here at this second spot right here, you have to have 55 gallons flowing through per second. The volume going through over here equals the volume going through over here. Think about it, people. Think of the logic. Let's say over here you thought, well, it's a skinnier pipe. Maybe you only have like a smaller bit going over there. Maybe you only have 30 gallons. Whoa. Maybe you only have 30 gallons per second going over here. But think of the logical problem there, people. If second after second, minute after minute, you have 55 gallons per second going through the pipe over here, what's the problem with only having 30 gallons per second going over there? Where did the rest of it go? Perfectly said. Where did the rest of it go? It's not like just disappearing. It's a closed pipe. It's like every second, like, uh-oh, what's happening? And on the other hand, if over here, for some reason, if you thought, oh man, there's going to be 100 gallons per second going over there because that spot's really cool, then what's the problem with that thinking?
Wrong.
It's just wrong. Where did it come from? Where's all that extra water coming from? It's only being fed 55 gallons per second. How could you possibly have? So it kind of makes sense. It's called the equation of continuity, and it basically says, however much, love that little eraser, huh? However much volume you have over here, that's how much volume you have over there. Okay? So let's look at the nitty-gritty, the formula, shall we? So, basically, rate of volume flow through one area equals the rate of volume the rate of volume flow through one cross-sectional area equals the rate of volume flow through a second cross-sectional area. Now, of course, that's a pain to write out all those words, and also, we're going to write that same thing out in symbols. And anytime you see that word rate, it's going to be something divided by time. If you wanted to calculate the rate at which I'm talking, you couldn't just say, oh yeah, 57 words. Is it 57 words per minute? Per hour? That would determine the rate. Anytime you have rate, that's like a how fast It's some measurement divided by time. And since this is the rate of volume flow is going to be the number of gallons per second, the volume per time. So if we wanted to write this as a mathematical formula, basically this becomes the amount of volume, the change in volume over time at, one section of the pipe equals the rate of volume going through the pipe at another section. So this is the volume per time in one section divided by the volume per time in another section. And this particular thing, volume per time, or change in volume per time, is called the volume flow rate. So you could say the volume flow rate, at one cross-sectional area equals the volume flow rate at another. Volume flow rate at one section equals the volume flow rate at another section. And what we're going to do now, though, is take a close look at how you can calculate volume flow rate. Of course, you could just take the number of gallons or the number of cubic meters, as we use in science, metric, divided by the number of seconds. But there turns out to be another way of calculating volume flow rate. So, let's take a look, shall we? How can volume flow rate be calculated? All right, so let's draw a pipe. And let's say we have a little tiny volume of pipe So we have this little volume of liquid going through the pipe, yes? And let's say that we're going to measure how much time it takes, that little volume to go through that little section right there, yes? Well, volume flow rate is the volume that goes through the pipe in that little amount of time. But the volume of a cylinder could be stated like, how if it was a cubic type structure, it would be base times, or like length times width times height. Well, since it's a cylinder, the volume will be the area of the base of the cylinder times the height of the cylinder. And I know this is like a cylinder on its side, so the area of the base of the cylinder would be like this little in here. Yes? And then the height would be from here to here of this cylinder. So, another way of saying volume flow rate, the volume per second, it's going to be the area of that base, and I'm just going to call that A, the area of the base, times the little height of the base, yes, divided by how much time it takes, that little height of the little cylinder of water to go through the pipe, yes? And I'm going to make some room in here. And I can rewrite that, folks. The volume flow rate, the volume per time, equals that little cross-sectional area, the area of the cylinder, times the height of the cylinder, divided by how much time it takes, that height of the sideways cylinder to go through the pipe like that, yes? But do you recognize this right here? Height per time. And remember that height, that's just this little right here, from here to here. That's the distance from here to here. Basically, what is that going to represent, the height per time there? It is a rate. I'm looking for a specific rate. That's the velocity. That's how fast that sucker is going through the pipe. That's the velocity. Remember, velocity equals displacement over time. What's the displacement forward? H over how much time? T. So basically, folks, if I take the cross-sectional area of the pipe, and I multiply by the velocity of the fluid going through the pipe, that tells me the volume flow rate. Who knew? Who knew? If you take the cross-sectional area of the pipe, how much area the pipe is made out of, and you multiply by the velocity of the fluid going through the pipe, that tells you how many cubic meters of fluid is going through the pipe each second.
Yeah, which one's long?
Ooh, I'm so glad you pointed that out. This V over here is volume, and this V over here is velocity. So now we can jump back over here. And remember we said the volume flow rate through the pipe at one point equals the volume flow rate going through another point? Well, here's how the equation of continuity is popularly seen. This is the bottom line equation that you're going to end up memorizing and applying. Here we go. Let's write it out. The cross-sectional area of the pipe at one point times the velocity. Velocity is a lowercase v, where volume is a capital V. And I know it's kind of hard to see from my notation here, but this right here is a velocity at one section equals the cross-sectional area of the pipe at another spot times the velocity of the fluid at another spot. So, folks, check this out. If the pipe goes from fat to skinny, and this value here gets a lot smaller, yes? If it's a skinnier pipe where the cross-sectional area went down, well then what's going to happen to the velocity of the fluid going through that section of the pipe, Shira? It's going to increase. So if we go back one more page, maybe another one, right over here, right? We know over here the fluid is going to have to be going faster through there. And over here, it'll be going slower. And last but not least, we can look at a typical AP question. Here we go. They give this pipe here, and the diagram's kind of small, but basically here's the pipe, and you're comparing three cross-sectional areas, here, 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 and they tell you that, A2, right here, that is the middle one. That's where the pipe has the biggest cross-sectional area. That's right, people. That's where, very wide diameter pipe. And then they tell you that A1 is a lot smaller. Okay, so A2 is 4 times A1. So this one over here is A1. And if you take A1, you multiply by 4, you get A2. And then A3 over here is even smaller yet. If you take that little cross-sectional area, A3, and you multiply by 8, then you get the cross-sectional area of A2, yes? And it says, how do the velocities compare? So basically what we want to do is figure out, well, how does the velocity at 1, compare to the velocity at 2? Yes. V1 is definitely going to be smaller than V2. Great initial understanding. Now what we have to do is actually say exactly how much smaller. And it is going to be a quarter as much. Okay? Now, let's see if we can figure out how to solve this, mathematically. Okay, so we know that, all right, let's stop here, folks. Thank you very much, guys. Happy holidays. So we know that A1 times the velocity V1 equals A2 times the velocity V2. And we know that A2, though, A1 times the velocity V1, we know that A2 right here, as it says up here, is 4 times the cross-sectional area of A1. So that's going to be multiplied by V2. And then we see how basically, regardless of what A1 is, A1 cancels out. Okay. V1 is going to equal 4 times, this should be a V2 over here, V2. Or you could say that V2 equals 1/4 V1. As you said. And then you could go back and do the same sort of thing for the third cross-sectional area, which I'll leave up to you. So, bottom line, equation of continuity. Amount of volume going through one section of the pipe equals the amount of volume going through another section of the pipe in the same amount of time. Okay. 2 equations you need to know. Change in volume over time in one section equals the change in volume over time in another section, and this here is volume. And cross-sectional area times the velocity equals cross-sectional area times the velocity. Thank you very much. One last thing, mass flow rate can also be determined. Mass flow rate would be the amount of mass flowing through the pipe per second. But recall that density equals mass divided by volume, big capital V, yes? So if you solve that for M equals density times volume, yes? So mass flow rate, mass per time, basically can be rewritten, what you call it, right here. This is going to be density times volume. So basically the mass per time is going to equal the density of the fluid times the volume per time. Or I could rewrite it this way: density times volume per time. So, let me make some room here. Mass flow rates equals the amount of mass per time, which equals the density of the fluid times the volume flow rate. Well, we know what the volume flow rate, that's the area times the velocity. So the mass flow rate is just the density times the cross-sectional area of the pipe times the velocity. And in this case, the little v is velocity. Mass flow rate.